Okay, so we're going to talk now today about specifically convex optimization problems and how to model certain problems as convex optimization problems in different standard forms. So that will be approximately the first half, and then the second half of today we'll talk about duality and how one can check whether a solution to an optimization problem is optimal or not. Okay, and you'll be happy to know that I figured out why I was randomly moving through the slides yesterday. I don't think I'll do that today. Okay, so yesterday we said, I think this was just before the end, we said we have this optimization problem, which is now a convex one. So we have some convex objective function f, 0. We have a bunch of inequalities, which may or may not be linear inequalities. There might be other nonlinear functions, provided that these fi's are convex functions. And then we have a bunch of equality constraints. And if every component of this is a convex function, we have a convex objective and convex constraints, then we say we have a convex optimization problem. And the nice thing about this problem is that every locally optimal solution is globally optimal. And I said yesterday, okay, when you have an optimization problem, it's not always clear that it should look like this. Okay, so sometimes you have to work hard to make it look like this. And then I think we did this one yesterday. Yeah, that was the last one. Okay, so we just said, you know that a convex optimization problem has every locally optimal solution is globally optimal by just making a little argument about f being a local optimizer, and then you make some argument about what the function looks like around, or sorry, x being a local optimizer, and then you say something about what the function must look like around there, and then you suppose that there's some other point far away which is even better, and then you conclude that this cannot possibly be a convex function. Okay, so this is, if you like, a kind of cartoon about why local optimality must be global optimality for a convex problem. Okay, so now what I want to show you are some conditions that you can use to check whether you have a globally optimal solution or not. Okay, so the first one is this one. So first of all, you know that if you have a convex optimization, if you have a convex function, then a condition that I guess you'll be familiar with is this one right here, that the gradient of the function at the point that you're claiming is optimal must be 0. Okay? This is not true. This is not an optimality condition for any function, but just for convex one. So it says that assuming that your function is differentiable, your function is shaped like a bowl, and the point that you found here is the flat part at the bottom of the bowl. Okay, if it has no constraints in it. Now, if you have a constraint, then it's not really clear that the optimal solution within the constraints will actually be, if you like, the bottom of the function. So if you imagine you have over here this function with level curves, which are these dotted lines, and the function is decreasing this way, then maybe the unconstrained optimal solution is down here. Okay? But if I take the gradient of this function, the gradient of the function at any point is always pointing uphill. Okay? And if I had an unconstrained optimal solution, then the gradient would be 0. If I have a constrained optimal solution, then what I find is that if I suppose that this point is the optimal one, then I find that the gradient of the function, or the negative gradient of the function, which is pointing downhill, has to point in the opposite direction of a vector pointing towards any other point in the set. Okay, so if I draw here a line like this, okay, this vector is y minus x. Okay, that's the vector pointing from x to anywhere else inside the set, and that has to be facing in the opposite direction of the downhill. Okay, and that's what this condition says right here. Okay, so if I take the gradient and I look everywhere, if I look at all the other points that I could go to, every other feasible y, if I conclude that every one of those points is uphill or going with the gradient, then I conclude that I must be at an optimal point. Okay, so that's what this says right here. Okay, so this is just one way to check if you have an optimal solution, or if you like, it's a geometric characterization of what an optimal solution should look like. And of course, it has to be a differentiable function for that to work. Okay. Okay, and so I can kind of generalize this to a number of different simple cases. So the one that you know already, I hope, is this one. So you say that if you have no constraints at all in your problem, then x is optimal if and only if x is in the domain of the function and the gradient at that point is 0. So you have some function which looks like this, and you just look for the flat bit right there. Okay, so unconstrained problems are easy. Now, as soon as you start to add constraints, then you have to start doing funny things to this function, the gradient of f. So if we take the problem of minimizing f0, and we add a constraint which says that x has to live in a hyperplane, so ax has to be equal to b, then I claim to you that x is optimal if and only if I can find some vector nu, that's that guy, that satisfies this condition. Okay? Do you believe me? Is it obvious why that should be the case? Okay, no. It doesn't. Okay, it's not. Okay, so I try to draw you a picture of why this is true. Okay, so my claim is that if I have an equality constraint, then I have a condition this has to equal that for some nu, okay? And so what this says is that the gradient now all I said was that there had to exist some vector nu that makes this true, okay? So that says that this gradient has to live inside the image of the matrix A transpose. Okay, that is to say there's some combination of the columns of A transpose that add up to this gradient. Okay, and well, if it's an element of the image of A transpose, then it must also be orthogonal to the null space of A. Because the null space of a matrix is perpendicular to the image of its transpose. Okay? So now if I try to draw you a picture, oops. What this says is that if I have my plane, okay, here's the hyperplane that I claim x has to live on, and I pick any point x here, okay? And I suppose that x is a solution to ax equals b. Okay? Then I should ask, what are all the other points in the plane? All the other points in the plane are just x plus any vector in the null space of A. Okay? That characterizes the whole plane. And now what I'm saying to you is that the gradient here, I'm saying the gradient has to be perpendicular to every one of these changes that I can add to x. So basically what it says is that the gradient has to stick straight out of the plane. That's all it says. So what this says is that if you have a plane, then the gradient of the function has to point straight out of the plane. Okay, can I go back? Objects. Okay, and then another condition I can state when I have an inequality constraint, so here I have sort of the simplest one, is that if I have x being non-negative, then x is optimal if and only if these two complementary conditions are satisfied. If the gradient of the function, or the ith element of the gradient, is greater than or equal to 0, then x has to be equal to 0, which says something like, when I find myself at a point where the gradient is not 0, I have to be up against the bounds. And if I find myself at a point where x is, or a component of x is bigger than 0, then at that point the gradient has to be flat. Okay, so if I draw you a picture of that one, it says something like, imagine I have a function of two variables. Okay, and the level sets of my function are like this. Okay, and then I draw the gradient of this function. So the gradient of the function would be pointing straight up at this point. Okay, so the gradient of the function in the x2 direction, this one, is non-zero. Okay, so it really wants to continue going downhill this way, down. Okay, but it can't because it's up against the bound. Whereas the gradient of the function in the left to right direction is 0, and so therefore it's okay that I find myself with a non-zero x1. Okay, this is all it says. And we'll see in towards the second half of today that there's a nice way of generalizing all of this into a more elaborate geometrical set of conditions. Okay, but this is just to say that one can make arguments about what the gradient of the function looks like and how it compares to the gradients of the constraints. Okay, that's all I want to say for the moment. Okay, so now let's talk a little bit about modeling of optimization problems. So when I say that I have some problem, I keep saying, well, you can maybe solve it in some equivalent way with doing a change of variables or adding some variables or whatever. So we say that two problems are equivalent, and equivalent is not any sort of strictly defined term, so informally called equivalent, if when I solve one problem, I can easily obtain the solution to the other problem. Okay, and what this means is that if I have a problem which is in some kind of inconvenient form, maybe I can add a few variables or change variables a little bit, solve a different problem, and then just unwind all the changes and get the solution to the first one back again. So I just give you two examples of this, two easy ones, because they're ones that get used a lot. So first of all, suppose that you have a function like minimize f0 of this affine function of x. Okay, so it's not f0 of x, but it's f0 of an affine function of x. This is a composition of an affine function with a convex function, so the objective is still convex. And likewise here. Sorry, this should be less than 0 here. Okay, and this one as well. Okay, so suppose that I have a problem that looks like this, then, well, maybe it's not so convenient to have these linear terms inside my functions. Okay, fine. So what I do is I take aix plus bi, and I make a new variable, and I call it y. Okay, and I add that as an inequality constraint, and then I just make this inequality f of y less than 0. Okay, and you might say, well, that wasn't too smart because now I have a lot more variables than before. Okay, and this is sometimes actually quite a good idea. Okay, so you'll see when you come to the predictive control part of the course that sometimes you have an optimization problem which is some limited number of variables. Maybe it takes a long time to solve. And if you introduce extra variables in some clever way, with some understanding of how your solver is going to work, then making the problem bigger means that you can solve it faster. Okay, but you'll see that in a few days. Okay, this isn't a promise that that will work. It's just sometimes that will work. Okay, but the point is that you're free to add extra variables through equalities as much as you want, because adding equality conditions doesn't change the convexity of the problem. Okay, and then the other common thing that you see, and again, there's a mistake here. This should be x. The other common thing that you see is that if you have a problem with an inequality in it, like this, and the inequality is not element-wise on x, okay? So it's not x greater than or equal to 0, it's just some function of x less than or equal to some vector. Then what you can do, if you want, you can add variables s, which complete this thing into an equality. So I add some si, which is greater than 0, And I make the first one an equality, and then I claim that this s term has to be greater than or equal to 0. So s is called a slack variable. Okay, now why would I want to do this? I might want to do this, for example, if I have a solver that doesn't like this kind of condition, but it likes that kind of condition. Okay? And there's no particular reason why I should solve it in this form than in that form, other than I might find that the software I have only accepts this, and my problem only looks like that. Okay, so fine. You just add a few variables. You get the problem into the whatever format your solver wants, and you solve it. Or, as I said yesterday, you give your problem in this format to CVX or YALMIP, and it figures all of this out for you. That's a better option. Okay. Okay, so now we'll talk about linear and quadratic programs, because these are the two types of optimization problems that you'll see most often, and particularly you'll see most often in predictive control. So we said already yesterday, I think this slide is exactly the same as the one from yesterday, because it's important that you see it twice. A linear program is one where you have a linear objective function, and you have all of your constraints made up entirely of linear functions. So you have ax equals b, this is a plane, okay? And then you have gx less than h, this is a collection of half spaces. So you have to think of this thing as being an element-wise inequality, and you take every row of g times x is less than or equal to one of the elements of h. And this gives you a hyperplane. Okay, you have to satisfy all of them, so you have to be on the intersection of the hyperplanes. So one of the rows would define a line here. You get everything to one side. Another row would define a line here. You get everything to one side. And the result is that the feasible set is the interior of this region. So you get a polytope as your, or you get a polyhedron as your constraint set. This happens to be a polytope because it's bounded. Okay, so the feasible set of this guy is polyhedral, and if you want, you can keep the d in there or not. It's up to you. It doesn't do anything to the optimal solution. It doesn't change what the optimal x is. But if you drop the d, then solve the problem. Don't forget to put the d back in when you say what the optimal value is. Okay, so this is one standard form. So many LP solvers will accept a problem in this format. The other way that linear programs can be defined is like this. It's not really any different. You say I have a linear function. I dropped the constant term here. Doesn't make any difference if you keep it or not. And I say I have an equality constraint ax equals b, and I have an inequality which is a non-negativity constraint on one of the variables. Okay, and the feasible region looks exactly the same. It's a polytope. Actually, in this case, the feasible region would be the set of all non-negative variables, which is the positive orthant, okay, which is like a cone-shaped set, and then you take ax equals b, which slices through this set some plane. Okay, and well, why should you prefer this one to the other? There's absolutely no reason why you should care which format you end up with, other than maybe your solver likes this way or maybe your solver likes the other way. Okay, and well, I'll come back to this in a moment. The thing to remember is that if you have an optimization problem which does not look like a linear program, okay, it doesn't fit exactly this mold or the previous one, in many cases, it's possible with a bit of effort to make it look like this. Okay, and I'll show you an example in a moment. So in particular, if you have any function which is like an absolute value here, okay, this doesn't seem like it's linear, but you can, through inclusion of extra variables, make it into a linear program. So we'll do that in a moment. And if you find that your problem can be rewritten like this, then you're usually in a pretty happy place because there's lots of different software tools to solve this problem for you. Okay, so now I just want to look, if you look at this one, I have here one inequality, which I can even write like this. I can write it as minus I x less than 0. Okay, that's the second one of these. Okay, I just make it a left-facing inequality. So now I have an equality constraint and matrix times x less than 0. And this looks exactly like that one. Okay, so I just take g to be minus I and I take h to be 0. Okay, now my claim is that I can write this one in such a way that I have an equality constraint only and variables which are non-negative. Okay, I just want to convince you that I can go back and forth. Okay, so it's very easy. What I have to do, I'll just take the inequality constraint. Okay, leaving the other bits out. So if I have a condition like minimize C transpose X, and then I have Gx less than H. Okay, what I want to do is now this doesn't have any equalities in it at all. Okay, so what I can do is, first of all, I can complete this inequality with a slack, like I did before. And then I still have the difficulty that the x could be positive or negative. Okay? So what I do is I just split x up into its positive part and its negative part, and I add a slack, and then I'm finished. Okay, so I do it like this. I say, instead I want to minimize C transpose times the positive part of x, so upper bar means the positive part, and then I subtract C transpose times the negative part. Okay? And then for my constraint, I make my constraint Gx, the positive part, minus Gx, the negative part, plus S greater than 0. And then I just add a constraint that the positive part, so that when I say the negative part, I mean the absolute value of the negative part, and S, these all have to be bigger than 0. Okay, so now this problem is in the other form, which has an equality constraint. Oops, sorry. Yeah. No, it doesn't. Yeah. Okay, like that. So now it has an equality constraint and all the variables are non-negative. So if I have a solver that only accepts problem descriptions with non-negativity and equality constraints, then what I do is I solve this guy. Okay? And then when I want the solution back up here, I just take x to be equal to x minus x, like that. Okay? Done. Now this is kind of a pain, right? I don't really want to have to do this every time I solve my problem. So if I can advertise to you one more time, don't actually do this. Okay? Type your problem this way into CVX or YALMIP, press solve, and it will do all of this for you automatically underneath. Okay? That's the easier way to go. Okay. Right, so now what I want to show you is just some example linear programs and an example of cases where you can turn something that doesn't look like a linear program into something that does. Okay, so this is, okay, maybe you'll guess it's not really a serious example. This is the cheapest cat food problem. Okay, so I have a cat. I don't like my cat very much, so I want to feed it at not very much cost. Okay, so I have a bunch, I want to make some cat food and I want to choose some quantities of ingredients, I don't know, fish, meat. It's a minimization problem, so probably other stuff that's less good for cats. I don't know, vegetables, whatever. So I have a bunch of quantities that I want to pick of different ingredients, and every ingredient costs, say, per kilo CJ units of money. Okay, and what I want to do is minimize the sum of all the costs. Okay, now, oh, that's easy. I just don't feed my cat anything. Fine, okay, the cost is 0. But then I have, you know, because of various legal requirements maybe, some rule that says I have to actually feed my cat, so I have to give it the right combination of nutrients to add up to a certain level. So it has to have a certain amount of protein, carbohydrate, whatever. So every ingredient that I pick has a certain level of each nutrient, and I multiply them all together, and they have to reach some threshold value B. Okay, so that says that A times X has to be greater than or equal to B. And I'm not allowed to pick a negative amount of any one of the ingredients. Okay, so if I have all the data of this problem, I know how much everything costs, I know the nutritional content of every type of food, and I know what I require, then I just solve this problem, I buy all the stuff, I mix it together, and I feed it to my cat. Okay, and then that was the cheapest way to do it. Okay, and this is a general example of what's called a resource allocation problem. So I have some money, I need to allocate it to a bunch of resources in an efficient way, and I have a bunch of constraints that I need to apply to those resources. And, well, it seems easy. These two guys, Kantorovich and Koopmans, they won Nobel Prize in 1975 for figuring this out. Okay, they didn't figure it out in 1975. They figured it out in the mid to late 30s, and that's because this guy here, Kantorovich, he wasn't interested in feeding cats. He was interested in feeding Russians, and he wanted to allocate the budget of the Soviet army in such a way that he fed all the soldiers in the most efficient way possible. Okay, and he was definitely minimizing cost and not maximizing flavor. Okay. Okay, so, and you see many different problems in economics can take this kind of form. Okay, so this is an example of a problem where I can just take my problem description and it just naturally falls into place as a linear program. And these guys spent, okay, I don't wish to underplay their contribution, okay? I mean, they figured out how to write this type of problem like this, but then more importantly, they figured out how to solve this problem, okay, which is more difficult. Okay, but the point is that this is naturally a linear program, but there are other problems which are not so obviously linear programs, but which turn out to be rewritable in this way. So I'll show you a few of those. So suppose now that I have a function where I want to minimize the maximum value of a bunch of linear functions. Okay? So my objective function now is this whole thing, including the max. This is f0. Okay? And this function looks kind of nasty, okay? It's not differentiable. It's a convex function because it's the pointwise max of a bunch of functions. But it's not linear and it's not differentiable. So it's not really clear what I can do. So what I can do is, first of all, I draw a diagram down here of this function. So I have down here, I take each one of the functions. Each one of the functions is linear. Okay? So I have that one, this one, and so on. And I want to evaluate it at a certain point x. So what I do is I draw a straight line up from x, and I look at where all of these lines intersect this vertical. So the leftmost one intersects it here, the rightmost one intersects it there, and another one intersecting here, and then the highest one there is coming from the third piece. Okay, and so the value of this function is this value, because that's the max of the four pieces. And I claim to you that I can rewrite this optimization problem as a linear program. So first of all, I point out to you that I can even include this extra inequality constraint, which would tell me something like the domain over which this max function is interesting to me. Okay? And I also claim to you, which I won't show you, is that if you have any convex and piecewise linear function, you can always write it as the max of a bunch of functions like this. So if you imagine that I have a convex function and every piece of it is flat, okay, then I can always write down a bunch of planes and then take the max of these planes, and that would describe my function exactly. Okay, and I claim to you that this function, or this problem, can be rewritten as a linear program. Okay, so I'll show you how to do it. Well, it's actually really easy. So what we do is, we take this function, okay, the inner part, the thing that I want to minimize, is the max of a bunch of functions. So the trick is to rewrite the problem in epigraph form. So remember that the epigraph is the region above this blue curve. The blue curve is the function I'm trying to minimize. Okay, and the epigraph is every point that's above this blue curve. Okay, so I want to add one variable which tells me how far above the curve I am, and then I want to minimize that height. Okay, so I do it like this. I say that I'm going to take a new decision variable, and I'm going to call it t. I'm going to minimize t. Sorry. So minimize t, and then I get rid of this. This is no longer my objective function. Now what I do is I take this max function and I make it less than t. Okay? So this was the thing that I wanted to minimize. And now instead of minimizing it directly, I minimize some upper bound of this function. Okay, so I just put a variable above. I push down as far as I can. And that's where I get my objective function from. So we would say that this problem now, with the 3 lines, is written in epigraph form. Okay? And so now all I have to do is I have to do something about this constraint. So it says that the max over I of each one of these linear functions has to be less than t. Okay, well, if t is bigger than the max of all of these things, then it must be bigger than each one individually. Okay, so it's bigger than the first and the second and the third and so on. So I just go down here, I say now my new problem is minimize t, subject to each linear function being less than t. Okay, and I just push down t as far as I can. Now this is a linear program, because I have a linear objective, which is just actually scalar, it's just minimizing one of the elements, and I have a bunch of linear inequalities. And here in the second line, x is a decision variable, and t is a decision variable. So if I want to write it in standard form, I have to actually write down my decision variable like this in a new vector with one extra term, and then I have to rewrite it all such that all the variables are on the left. Okay, but this is just manipulation. Okay, so this is a really nice trick. Okay, and it's a nice trick because there are many functions, particularly the norm functions, the 1 and infinity norm, that I can write down in this way, in this max function way. Okay, so we'll do that and then we'll stop for a few minutes. So suppose that I have a problem that looks like this. So now what I want to do is I want to pick some x which lives in the smallest possible box and which satisfies fx less than g. Okay, so I'm trying to minimize the infinity norm. This is the magnitude of the largest element of x, or the largest absolute value of the elements of x. Okay, so I want to minimize this thing, and I want to satisfy some other inequalities. Okay, so what I can do is this infinity norm I can write as a max function like this. So x may have positive and negative values, and I want to minimize the largest absolute value. So what I do is I write down a list of all of the components of x, which may be positive or negative, and then I write down a list of all their negative entries. Okay, so if one of these is negative, then its counterpart over here will be positive. And then I just minimize the biggest number in this list. Okay, and then it should be clear that I would be then minimizing the size of the largest absolute value entry of x. Okay, is that clear? Okay, so then, right, so now I have minimized the maximum value of this great big list of linear functions. Okay, each entry by itself is a linear function, subject to some constraints. Okay, so I use my trick from before. I minimize t. I write down a big list of all of my linear functions, which is just each x by itself, and then each minus x by itself. I put a number t above each one of those, and I push down t as far as I can. And okay, I get a linear program. I get this guy. And what I've written here, okay, this is exactly the same as that, except now what I've done is, first of all, I've taken this guy, and I want to write it just as a single inequality for x. So I take the vector x, and I make it less than or equal to a vector of 1s that's long enough times t. So this just says each element of x is less than t. Okay? And then I've just combined the left-facing ones and the right-facing ones into a single pair of inequalities there. And now if I look at this problem by itself, what it's saying is take x, which is a vector, put a vector of 1s to its left and a vector of 1s to its right, okay, or outside, and then just squeeze down as much as I can until x is in the smallest possible box. Okay, so this is a linear program because it has only linear inequalities in it. And so now I should ask, what is this t doing? It's bounding the absolute value of every element using a single number. Okay, so it's pushing, squeezing down the absolute value of every element with a common term. That's what this guy does right here. Okay, so this is giving us a nice linear program to solve. And then the counterpart to this would be the one norm. So the one norm says take the absolute value of every component of a vector, and instead of taking the biggest one, just add up all the absolute values instead. Okay, so now I want to show you that you can turn this one into a linear program also. So, okay, now what I want to do is write this as a max of linear functions. But the problem is that up here, I have the sum of absolute values. Okay, so now I have, instead of a single max function, I have a sum of max functions. So what I do is I take ax minus b. If I look here, ax minus b subscript I means compute this vector and take the ith term. Okay, so if I take just the first term, I take the first term and minus the first term. I take the max of those two things, and I have the absolute value of the first term. Okay? Then I add up over I all of these absolute values, and I get the one norm. And I have still my polyhedral constraint. Okay, so now this is, instead of just a max function, it's a sum of max functions. And so instead of bounding from above this whole thing by a single number t, what I should do is I should bound every component from above with its own number t, or ti. So now what I do is I take each ax minus b, so I take the first element, and I upper bound it by some number t1, and then I change the sign, and I upper bound that thing by t1 also. I do this for every I, and then I add up all the bounds. Okay, and then I claim to you that if I minimize the sum of these bounds, I've minimized exactly the one norm of this vector. And again, I can write it into a compactified form by taking t1 through tm, writing it in a single vector, which now I call t again, except now t is not a scalar, t is living in Rm. And 1 transpose times t should be the sum of these things. And what I do is I push down on the vector ax minus b from above with t and from below with t, except now because t is a vector instead of a scalar, I have some capacity to individually tighten on every element. Okay, so this is minimizing now the one norm. And again, it's a linear program because everything is linear. Okay, and if I look down here, before with the infinity norm case, what I did was I picked a single value, a single scalar, and I tried to compress it around the whole vector x. And now what I do is I take a vector of these bounds, t, and I try to push down element-wise on the vector that I want to minimize. Okay, but in the end, it's basically the same type of problem. It's a linear program. Okay, and I can solve it with some standard solver. Should we stop now or do... Let's stop now for 10 minutes. So 5 past, we come back. Okay, so we'll start again now. So we spent a couple of minutes discussing linear programs and all the different, not all the different, some of the different ways of converting different common types of problems into linear program format. And now we'll do the same for quadratic programs, briefly. So okay, so a quadratic program is one that looks just like a linear program, except I add one extra term, which is this x transpose px term. And I have to have the matrix P being, I've written here, in S superscript n subscript plus, which means S has to be a positive semi-definite matrix. So S means that it's symmetric, n means that it's n by n, and the plus means that all of its eigenvalues are non-negative. Okay, so what that means is that this function, x transpose px, is a convex function. And I add a linear term onto it, and I have the sum of two convex functions, so the objective is also convex. And the feasible set I still take to be the intersection of a bunch of half spaces with some plane. So the problem looks, in terms of the feasible set, exactly the same as before, except now I have the level sets of my function being these nice oval shapes, okay, where the orientation of this oval is determined by the eigenvectors of P, and the scaling of the oval is determined by the eigenvalues of P. Okay, and I can also, if I want, maximize a quadratic function, provided that minus P is a positive definite matrix, which just says that I can, if I have a concave objective function and I want to maximize it, then I just change the sign and I minimize it. And then at the end, I don't forget to change the sign of the value that I get. Okay, now, this type of problem is not really any more difficult to solve than a linear program. And I just want to show you some cases where you end up with a problem that looks like this. And in particular, I want to point out to you that when you solve a linear quadratic optimal control problem in the MPC part of the course, you're going to end up with a problem that looks exactly like that. Okay, and your variables will be the states and inputs of your system, and they will be related to one another through the dynamics in some equality constraint. And if the inputs have some bounds or the states have some bounds, you'll have some inequalities on these variables. And your objective function will be something like the sum of the squares of the states plus the sum of the squares of the inputs, or some scaling of this. Okay, so in terms of predictive control, this class of problem is by far the most common. Okay, so what are the different types of problems that you can write this way? So I mentioned the control problem. This doesn't have a closed form solution if you have constraints, but the most common one, or the first quadratic program ever solved, if you like, was this least squares fitting problem. So you have some x that you want to pick, and you want to make it you want to make ax minus b as small as possible in a least squares sense. So this would be some kind of linear curve fitting type problem. Okay, and there's an this is really the one happy case where there's an analytical solution to this problem. So you want to minimize the norm of this error, and you can just figure out that the analytical solution is the pseudo inverse of a times b. Okay, so you don't need to do any fancy optimization. You don't need any iterative software. You just put a/b into MATLAB, and it solves it for you. Okay, so there's a closed form solution. As soon as you add any constraints onto this problem, or just about any other problem with a quadratic objective, that's not true anymore, and you need some kind of numerical method to solve it. Okay, so even if you just put a very simple upper and lower bound on x, you cannot solve this anymore. Analytically, you can't solve it. So you need some kind of optimization method to solve it. Okay, so now I just show you two other types of problems that turn out to be quadratic programs. One is this funny looking one where I want to minimize the expected value of some cost. So think of C as being a random vector. Okay, I want to minimize its expectation. And then, well, okay, so first of all, just take the expectation minimization subject to some constraints. So if I change the sign here, I would have maximize the expected value. Okay, so I might have an investment problem where I want to maximize my expected return on some investment. So X would be the amount of money that I put into each of a number of stocks, and C would be how much I think that stock will be worth in 6 months. And I have some constraints saying that, okay, I can't invest a negative amount of money in each one, and maybe I'm not allowed to put more than a certain fraction of my budget into each one. And maybe I have some equality constraint between them for some reason. Okay, and I would have some expectation maximization problem. Okay, so this is, as an investment problem, maybe not such a good idea, because it may be that the stock with the greatest expected return also has extremely high variance. Okay, so what I can do is I can penalize the variance of this vector as well. Okay, so maybe I don't want to invest too heavily in things which have an extremely uncertain outcome. Okay, so now what I can do is I can assume that C has a known mean, which I call C bar, but C also has a known variance, which I call sigma. And then I can rewrite this thing like this. Okay, and gamma tells me how sensitive I am to variance. So if gamma is 0, I only care about maximizing expected profit. If gamma is huge, I only care about minimizing variance. Okay, so it should be clear that the expectation of this thing is just the mean value of C times X. And what about this guy? I would have here the variance is the expectation of X transpose C times C transpose X, okay, which is equal to X transpose times the expectation of C transpose times X, and the expectation of C transpose is just sigma, okay? So now what I have is I have an objective function with a linear term in X. It's not uncertain anymore because C is a known mean, and I have a quadratic function of X. And I know that the covariance of a vector should be a positive semi-definite matrix, okay? So that's C. So this is a quadratic program. And, well, maybe if people solve this problem more often than the one with gamma is equal to 0, then banks wouldn't crash so much. Maybe they would still. Okay, so this is, okay, and the point is that you even see this type of problem in control, because if I have some uncertain disturbance in my problem, and I want to minimize the expected value of a quadratic cost, then again, almost an identical situation would appear. Okay, and again, I get a quadratic program. Okay, and I show you one more. Now I can do quadratic, and I can do L1 or L infinity, and then if I want, I can mix and match. So now I can take a problem where I want to find a least squares solution to some problem. Okay, so find the x that minimizes the square of the errors of ax minus b. But then I say I want to also minimize the one norm of x. Okay, and what this would do is it would, in a sense, discourage having lots of small entries in x. So if I try to find the least squares solution, but then on top of that I put a penalty for making every component of x non-zero, then as I turn up that penalty, I'm discouraging non-zero terms in my solution. Okay, so I can remodel this problem in exactly the same way as I did before. I take the one norm component, I rewrite it in terms of some upper bound vector t, and then I try to squeeze the element-wise upper bound on x. Okay, and I might want to do this, for example, if when I solve my problem, I find that x has a few really big terms. These are giving me most of the, getting me most of the way towards optimality. And then I find I have lots of these annoying tiny little terms, and I want to make those go away. So I include this one norm penalty, and this has the effect, sort of heuristically, of giving me a sparser solution to my problem than I would have had otherwise. Okay, but it comes at the cost of having to solve this numerical problem rather than a least squares problem. Another thing that I could do is, instead of penalizing the one norm, I could just assign a budget to the one norm. So I could take this same problem again. I could delete this part from the cost. Okay, I could delete t as a decision variable. Okay. And then I just say that t is now a constant. Okay, and I've just restricted t to be inside a one norm. Sorry, this would be, okay, then I would have a constraint, rather, that 1 transpose t is less than some number. So now I have a kind of budget on the one norm, and I want to minimize the square. Okay, this is a variant of the other one. So if I have the problem with the one norm term in the cost, we call it Tikhonov regularization. And if I have the one norm constraint as a constraint, or a budget, then we call it the lasso method. Okay, but it's basically the same idea, which is to try somehow to get a slightly sparser solution to my problem. Okay, now this is not really so essential for control. The point is that there are many different ways, there are many problems that are not obviously linear or quadratic programs to begin with, but with a little bit of effort you can make them look the way you want them to look. Okay, so now we come to the, so I'm only going to do the the part 5 here. We're not going to do part 6. Part 6 is just in the notes for your, betterment, right? Or your interest. Okay, but we'll only talk about duality, and nothing in the exam or anything else in the course is going to have anything to do with what's in part 6 of the notes. Okay, it's just there for reference. Okay, so now what I want to do is we want to talk about what are the properties of an optimal solution to a convex problem, and how can I go about constructing an optimal solution to a convex problem. And I'm not going to show you any numerical method. I'm just going to try to show you some conditions that you can check to see if you have an optimal solution. And then when you come to the numerical part of the course, what you'll find is that the numerical methods all come down to finding points that satisfy the conditions that I'm going to show you. Okay, so let's go back to our original problem. It doesn't necessarily have to be a convex problem to begin with. We say that we want to minimize some function, f0, and we want it to satisfy a collection of these inequality constraints and a collection of these equality constraints. And now I've written on the side over here P. I'm going to call this problem P, and P stands for primal. Okay, so I'm going to write, first of all, my primal problem or my original problem, and then in a few slides we'll come to a counterpart for this problem, which will be called the dual. Okay, and they form a pair. So we start with just one side of the pair, which we already know about, the primal one. And let's suppose that I solve this problem, and I get an optimal value, and I call that optimal value P star. Okay, it's P star because it's the primal optimal value. Okay, so now what's difficult about this problem? The difficult thing about this problem, or one of the difficulties with this problem, is that it has a bunch of constraints. Okay, so minimizing a function is maybe easy. Minimizing a constrained function is usually hard. Okay, so let's just wish all that away, and we'll write down a new function called the Lagrangian, where I just take my original objective function, and instead of having constraints, I just take a linear combination of my constraint functions. Okay, so now I have a new function L, which is an unconstrained function of x. And I can think of, so what I do is I take my inequalities fi, I multiply each one by some number lambda, and I add them all up. Okay, and then I multiply each of my equality functions hi by some other scalar nu, and I add those all up as well. And so now I have a function of x for fixed lambda and v, which I can think of as just weights. But then I can ask, or I can think about this function as a function of both the x's and also the weights. Okay, and I call these weights the Lagrange multipliers for my problem. So I have two types. I have the inequality multipliers, which multiply the f's, and I have the equality multipliers, which multiply the equality functions h. Okay, so this is just a weighted sum of all of the functions in my problem. Okay, it's entirely unclear at the moment why anyone should care about this function. Okay, you can ask, how did Lagrange think of this? Probably he didn't start by just writing that down, I guess. Okay, but it turns out that this function is important because it's going to tell us something about when we have an optimal solution and when we don't. Okay, is it clear what's going on with this function so far? Okay. Okay, so now, why should you care about this function? So, suppose that I take my function L, okay, which I've written down here, and I hold lambda and nu fixed, and for every lambda and nu, I minimize over x. And I define a new function g, which has got rid of the x, by just minimizing for every lambda nu over x this Lagrangian function. Okay? Now I should ask, first of all, what are the properties of this function g? Okay, so what I have here is, if I think about this function holding x fixed, then this is just a linear function of lambda and nu. Okay, so this is a convex function of lambda and nu. It's also a concave function of lambda and nu because it's a linear function. And if I pick a different x, I get a different linear function. And if I minimize over x, I get the min of a bunch of linear functions. Okay, so I've drawn that down here. So, Okay, this is minimizing over x in what is probably an infinite number of points, because big X might be Rn, for example. Okay, but I've just written a few of the lines. So if I pick 1x, and this diagram only has one inequality constraint in it, but it's a general principle. I pick 1x, and I write down what this linear function would look like. Okay, so I get some linear thing, and then I pick a different x, and I get a different line. And I pick a different x, and I get another line, and so on. And then I take the min of all these things. And so my function will look like this. Okay, because now I have the pointwise min of a bunch of linear functions. And this turns out to be a concave function. So we said yesterday that the pointwise max of a bunch of convex functions is convex. Here I have the pointwise min of a bunch of concave functions, so it's concave. Okay, and so this turns out to be a nice function to work with because it's concave, and in a moment I'm going to maximize it. But for now, I just point out to you that if I fix the weights such that the lambda is greater than 0, then no matter what weights I pick, this function is always going to be less than p star. Okay? And how do I know that this is true? So first of all, suppose that there's some x star, some optimal solution to the primal problem that gives me f0 x star equal to p star. Okay, suppose that's the optimal solution. Now I pick some lambda greater than 0 and some nu, and I think about what is the value of this function. So first of all, so I'm minimizing this function over x. Okay, so I'm going to get a number that's less than the value of this function for every x. So I'll just pick one x, okay? And then g will be less than this function evaluated at that one point, because it's less than the function evaluated at every point. So I just pick one, and I'm going to pick this one. Okay? So I plug in x star into this function. X star is, because it's the optimal solution to the primal problem, all of the h's will be 0. Okay? Because these are the equality constraints. This term will be p star. And all of these fi's will be negative, because by definition, the optimal solution to the primal problem satisfies all of the inequality constraints. So every one of these will either be negative or it will be 0. And all of these lambdas will be positive, because I said down here the lambdas have to be non-negative. Okay, so that says that g of lambda and nu is going to be less than or equal to p star plus a negative number. Okay, so therefore g, lambda, and nu must be less than or equal to p star. Okay, and actually it might even be a lot less than p star because I only picked one value of x to check this function. But then I actually said minimize over the x's. Okay, but I know that at least for that one point, this will be true, and so therefore it's true for every point. And it might even get so bad that this function might even be minus infinity. Okay, so this lower bound might be good, it might be terrible. We don't know. Okay, but the point is for the moment that g is a concave function, and it provides for me, for every selection of weights, it provides for me a lower bound on p star. Okay, so let's just see how one goes about constructing this function and producing this, first of all, constructing the Lagrangian and then constructing the dual function. Okay, so here's a simple example. My primal problem is minimize the square of a vector subject to ax equals b. So I have only equality constraints here, and I should think of my equality constraint as being actually ax minus b equal to 0, because I want the right-hand side to always be 0. Okay, so my Lagrangian is just going to be the function plus my equality functions times some weight. Okay, that's Lagrangian. So this, I have nu transpose times this thing because I have a vector of weights times a vector of left-hand sides of my equalities. Okay, and this just adds them up one at a time. Okay, so this is the Lagrangian, and now we say, what's the dual function? The dual function is the minimum of this thing for each nu over x. Okay, so I imagine that I'm holding nu fixed. I differentiate this function with respect to x because I want to minimize it, and it's an unconstrained function in nu. So I differentiate it, I set the gradient to 0, so here's the gradient, 2x plus A transpose nu. Okay, I solve this, it's easy. I get some nice solution for x. And now I plug in for each nu, this is the optimizing x in that min problem. So I just plug it back into the Lagrangian and I get my dual function. G is this guy. And you'll notice that it's a concave function because A transpose is always a positive definite matrix, and I change the sign on the outside. So this is a quadratic function that's curving downward, and I get a different value for every nu. Okay, so you give me some nu, I plug it into this function, and that provides for me a lower bound on the optimal primal value p star. Okay, and so for some nus, this will be maybe close to that number. For some, it'll be really far away. Okay, and then you might ask, what's the best one? Okay, so let's ask what's the best one. So we ask what's the best one by saying, well, suppose that I'm restricted to choosing non-negative lambdas, and I have a concave function g, and I want to find the best lower bound for p. Okay, so I just look over all the lower bounds I have, and I find the biggest one. So I take the max over my multipliers of this concave function, and I have a constraint, okay, which is a convex constraint, that the lambdas have to be non-negative. Well, now, why might I want to solve this problem? I might want to solve it, or I might be able to solve it, because even if the function I started with is not a convex problem, even if the problem I started with is not a convex problem, if P is not convex, then D is always a convex problem. Okay, because I'm maximizing a concave thing, which is the same as minimizing a convex thing. Okay, so even if the primal problem is hard, I hope that the dual problem is easy. I'm not saying it's easy, I'm just saying I hope that it's easy. Okay, I hope. So this problem is a convex one, so I have at least some chance of getting an optimal value for it, a globally optimal value for it. And I know that the optimal value for it, which I'll call D star, should always be less than P star. And I know that because for every lambda and nu, this function is less than P star. And so the biggest amongst all of those bounds should also be less than P star. It'll just be the best lower bound. And I say that a point is dual feasible if I pick a combination of weights that's in the domain of this function g. So the domain is all the points where it doesn't take the value minus infinity, and the lambda is non-negative. And this constraint here, that the lambda and the nu have to be in the domain, this can sometimes, or maybe even often, be written down explicitly. So instead of having, here I should actually say maximize over lambda and nu in the domain of g, and instead I can just write down here as a constraint explicitly the domain of g. Okay, so I'll do that in a moment. Okay, so here's an example. This is a linear program, and I have an equality. I have a linear objective. I have an equality constraint, and I have an inequality. And remember that I should write these as actually ax minus b equal to 0, cx minus d less than 0. I should think of them in those terms. Okay, so what I can do is I can take first of all, I want the Lagrangian function, okay, this function L. So it's written here. This thing on its own is the Lagrangian. So what I do is I take the objective function, c times x. I take my equality constraints and I multiply them by a vector nu. And then I take my inequality constraint functions, and I multiply them by their own multipliers, lambda. Okay, and then if I want, so this inner part is the Lagrangian function, and then if I minimize it over x, I get the dual function. Okay, now what I do is I look in here, I want to minimize over x, but I've got a bunch of terms that don't have x. I have nu transpose times b and lambda times d. So I take these out, and I have now a function here, which is a function of x on its own. So I've tried to isolate the terms in x by themselves. And now suppose that I minimize this function over x. Okay? So if I minimize this function over x, holding lambda and nu fixed, if this term here is non-zero, and I minimize the dot product of that non-zero vector over products with x, then it's going to be immediately minus infinity. Okay? So the value of this function is minus infinity most places, except in those places where the left-hand term is exactly 0. Okay, so I just write that down here. The value of this function, when I minimize, is the two terms on the right in the case that the thing multiplying x is 0, and otherwise it's minus infinity. So the domain of the function g is all of the places where it takes on a finite value, and that's all of the places where nu and lambda together satisfy this equality constraint. Okay, so the domain is this hyperplane. And so what I can do is I can actually, when I solve the dual, I can just write this down explicitly as a constraint, rather than having to worry about what's the domain of the function. Okay, so now what's my lower bound? Well, I have p star. My lower bound is this function for every lambda and nu. So I have the condition that this number here, which is the value of my function on its domain, is less than p star every time lambda and nu are in the domain of the function, and lambda's non-negative. Okay, so I get a nice lower bound. And again, I should ask, what's the best lower bound? Okay, so let's find the best lower bound. So I take my function. This thing that I'm maximizing is equal to g lambda nu. That's the thing that I want to maximize. And I want to maximize it only over its domain, so I just put down this hyperplane that defines its domain explicitly as a constraint. Okay, and so now I have maximize a linear function, that's this guy, subject to an equality constraint, and also a collection of inequalities. So this is in my standard form where I have some of the variables non-negative and a bunch of equalities. Okay, so it's a linear program. So I started off with a linear program, this one, p, that's the primal. I found the Lagrangian, I minimized over x to get the dual function, I formed it into an optimization problem to get the dual problem, and now I have the primal and the dual pair. And the point of this last line is I started with a linear program, and I ended with a linear program. Okay, and this is not always the case. Not if I start with a problem of one type, it's no guarantee that the dual of that problem will be the same type, but in this case it did happen. Okay, and I'll show you in a moment that for a quadratic program it's the same. So here the primal is easy to solve, and the dual is easy to solve. Easy in the sense that there's software available for me to use. Okay, so here's a second example. Okay, because it's important to be comfortable with the sort of mechanics of this process. So I start with the primal problem, minimize the 2 norm of a vector, subject again to an equality constraint, just an equality constraint this time. And what I do is I write down the Lagrangian first. So I take the objective function and I subtract the equality constraint. So now this time, because it's an equality, I can equally write it b minus ax is equal to 0. Doesn't matter which way around I do it. So this time I've done it the other way around. So I have b minus ax. I multiply it by some multiplier. Okay, and I've multiplied it through here already. And now I want to minimize this thing over x. Okay, and so some of the time, minimizing this over x will give me minus infinity, and sometimes it'll give me some finite value. So when does it give me minus infinity? It gives me minus infinity whenever this vector is bigger than 1. Okay, so if I have, this is the length of the vector x, this is the projection of x onto some other vector. If the thing I'm projecting x onto is bigger than 1, then this term can be made arbitrarily negative. Okay? But if this vector is less than or equal to 1, then I just get the other piece, b transpose nu. Okay, so here's my dual function. The domain is just all the nus that make this true. And so I write down the dual. The dual is the component that I get there. I put that in the max. And I have a constraint saying that the 2 norm of this weighted vector has to be less than 1. And again, I have a lower bound. Okay, this number here is always less than p star whenever that constraint is satisfied. And what I'm trying to do here is I'm trying to find the best lower bound. And in this case, I started with a problem which was, well, it's not a quadratic program because I'm not minimizing the square. I'm minimizing the norm of something subject to inequality. And I've ended up with a problem where I have a constraint on the norm of something rather than the norm and the objective. So this is called a second-order cone program, and this one turns out to be a second-order cone program also. Okay, but terminology is not important. The point is I started with a problem in one form, and I ended up in a problem, again, in only this case, with a problem in approximately the same form. Okay, and finally, let's talk about the dual of a quadratic program, okay, because it's the same procedure more or less. Okay, it's here just so that you see it at least once. So now we take maybe just some inequalities this time and a quadratic objective function. And I've, for convenience, taken Q to be positive definite, not positive semi-definite. And I've done that because I want Q to be invertible. Okay, so I write down my Lagrangian function. That's this guy here. Okay, this function by itself is L. And all I had to do was I had to write my constraint as Cx minus d less than 0. Okay, so I've taken my objective function, that's these two terms. I've taken my inequality constraint, that's Cx minus d, and I've multiplied it element-wise by some weights, lambda. Then I rearrange, so this gives me the Lagrangian. Then I minimize over x, that gives me the dual function. And then I reorder the Lagrangian a little bit so I get all the components that have x in them separately. So now I have minimized a quadratic function of x, but now it's unconstrained. Before it was constrained, now it's unconstrained. So minimizing the unconstrained linear function is easy. I just differentiate it, and I solve for x. So if I differentiate this function with respect to x and set it to 0, then I get this equality constraint. So the optimal x, for every lambda, the optimal x has to solve this. Okay, and you can see now why I wanted Q to be invertible, because now I can solve for x easily. Okay, so let's do that. The solution is that. I just invert Q and put everything that's not x on the right-hand side, and I get some solution for x. I plug it into my function, and I get that the dual function is exactly equal to this quadratic thing. And in this case, the domain of the dual function is actually Rm. Okay, so there's no point at which this function becomes negatively infinite. Okay, it's finite everywhere. Okay, so I get a nice quadratic function. You can see that Q started off as a positive definite matrix. So its inverse is also a positive definite matrix. But then I have a minus sign on the outside, so the whole thing becomes concave. And so my dual problem is to maximize this concave quadratic thing, subject to the constraint that the multiplier is non-negative. And now I want to write down this problem. So this is a concave function. I have a minus and then a minus there. So I changed the sign. So I have a plus, okay, a plus, and then I minimize it instead. And then I gather up all the terms, and I get this quadratic function. So the dual in this case, I said before that the dual is a maximization problem. But if I just change the sign so that I'm minimizing minus the dual function, then I get a standard-looking min problem. Okay, but there's nothing mysterious about this. I could write this as max and just change the sign to get back to here if I wanted to. Okay, but now I have minimized over lambda this quadratic function, subject to the lambdas being non-negative. Okay, so this is a quadratic function. I have here, this is a vector that's multiplying lambda, so this is a linear term. This is a matrix with lambda on either side, so this is a quadratic term. And then I have also still this constant term, which if I wanted to, I could drop. But if I were trying to compute a lower bound for my primal problem, I should really be careful to remember that I drop that if I do that. Okay, otherwise I'm not going to get as good a lower bound as I could have done. And so the dual of a quadratic program is another quadratic program. Okay, that's nice. And let's see. Okay, so now let's talk about a harder problem. So maybe you should ask, why would I care about finding a lower bound at all? Because I just told you that if I have an LP and I solve it, I need to use some LP solver. And I said, well, I can use this fancy method to get a lower bound. And maybe that would be helpful, but then I end up with another linear program. And so maybe you ask, what's the point? I mean, you end up having to solve the same type of problem anyway. Okay, so here's an example where the primal problem is hard, but the dual problem is easy. Okay, because I said that the dual problem is always a convex problem, even if the primal one is not. Okay, so here I take, again, what looks like a linear program. So I call this the primal problem. I minimize C transpose times X. I have some inequality. But then I say that the domain of this function is the set of vectors X where each element is either -1 or 1. So if I forget about the n for the moment, if I have curly brackets -1, 1, that just means the set which is either -1 or 1. And then if I raise it to the power n, that means the set of vectors in Rn, where every vector is 1 or -1. Okay? So this just says every component of X has to be +or -1. So it's nearly a linear program, except I've got this terrible integer condition on it. Okay? So, well, what I can do is I do a little trick here, okay? Instead of worrying about this as a constraint, which requires a multiplier, which would not be so nice, I take this and I put it inside the domain of the minimization. Okay? So I don't have explicitly any multiplier for this constraint. Instead, I make it part of the domain. And when I write down the dual of my function then, when I write down the Lagrangian takes the cost function from my primal problem, and then it takes the explicit inequality constraint, so ax minus b less than 0, and it multiplies them by some multipliers. Okay, so in this case, my Lagrangian just has the, if you like, the nice bits of my problem in it. Okay, but then, okay, there's no free lunch in a sense. I have to still deal with this -1 and 1 component, but since that's part of my domain, I minimize over that -1, 1 set. So now when I construct the dual function, I don't have an unconstrained minimization, but instead I have an integer minimization. Okay, so this is my dual function, but now it turns out that minimizing this over -1 and 1 is easy. Okay, and it's easy because I have here a linear function of X. It's C transpose, or sorry, it's A transpose lambda plus C all times X. Okay, that's what you see here. And then I multiply that vector. I have A transpose lambda plus C X. I want to make that product as big as possible. Okay, and I can choose either -1 or 1 for each component of X. Well, I should choose X with a sign that agrees with the sign of the corresponding element of this vector. Okay, which means that I just end up adding up the absolute value of the entries in this vector. And so the dual function is just the 1 norm of that guy. Okay? But I'm minimizing it, not maximizing it. So I should make the signs come out to be negative. So I get a minus on the outside. And then I have this extra term out here, okay, which comes from the lambdas. It's got nothing to do with X. So now my dual function is this nice thing. And I can maximize it to get my dual problem. So I maximize over lambdas my dual function here, subject to the lambdas being greater than 0. And if I wanted to, I could instead minimize. I could change the sign. So I can make this plus. Oops. I can make this plus. Plus, plus, and then I make this min. Okay? Now I'm minimizing the sum of a linear function with a 1 norm, and I showed you before that that's a linear program. So in this case, a mixed integer problem in the primal, which is horrible, is much easier to solve in the dual because it's a linear program. Okay, so basically, yeah, the dual of a mixed integer linear program is a linear program without integers. Okay, this is nice. And actually, if you want, as an exercise, what you'll find is that if you go back to this problem and you change this second constraint to -1 less than x less than 1, meaning that you relax all the integers to be on the interval between -1 and 1, and you take the dual again, the dual is again this problem, the same thing. Okay? But okay, that's just something to try. Okay. Okay, so I said that it's always the case that when I take my dual problem, my problem D, and I maximize, I get some value, and I call the value D star. Because I'm maximizing over lower bounds, the best lower bound is always going to be less than or equal to P star. Okay, and this is always true. And sometimes it's true that the dual is easier to solve than the primal. So in this mixed integer case, the dual is easier to solve. Sometimes not, okay? But sometimes it is. And, okay, so an example is the dual of an MILP, mixed integer linear program, is hard, but the dual is an LP, that's easy. Okay, so maybe if I want to get a good lower bound, or I want to get a lower bound, I should worry about the dual and not the primal. Okay, but there's no guarantee that D star is going to be anywhere close to P. So this is always true. Sometimes the two numbers agree. Okay, this is really nice. This is really satisfying when this happens. Okay, so sometimes I take my dual problem, I get a bunch of lower bounds, and it turns out that the tightest lower bound agrees exactly with the primal optimal value. And when that happens, we have what's called strong duality. Okay, if it doesn't happen, we just say that it's weak. All the lower bounds are below. If the best lower bound is equal, then we say that it's strong. And, well, it's really nice when this happens. And we're very lucky that usually if I have a convex problem, this does happen. Not always, but usually. Okay? And we'll try to come up with some rule about when it will happen, which is a very easy to satisfy rule. So most of the time, if you have a convex problem, you have strong duality. And so the value of the dual is equal to the value of the primal. So if you just want to know what's the optimal value, and the primal is hard, you solve the dual, it's the same value. Most of the time, if you have a non-convex problem, you don't have strong duality. Okay, so that's not to say that every non-convex problem doesn't have strong duality, but most of the problems that you will ever encounter, which are both non-convex and have strong duality, are tricks in a textbook to prove that not all non-convex problems aren't strongly dual. Okay, if you give me any actual non-convex problem and ask me to solve it, it's an extremely good bet that strong duality is not going to hold. Okay, just like with a convex problem, it's an extremely good bet that it will have strong duality. Okay, and so what we want to do is we want to, for convex problems, write down some conditions that guarantee that these two numbers agree with each other. And then we want to use those conditions to help construct a method of solving problems by finding optimal solutions to both the primal and dual at the same time. And what you'll see is that most of the optimization methods that we have involve solving these two guys together. Okay, so let's talk about strong duality. So suppose I have a convex problem. I write down the primal. So I have minimize a convex function. I have some convex inequalities, and I have some equality constraints, which make up a hyperplane. And I want to know, does P star equal D star? Okay, that's what I want to know. Well, the answer is that I can tell if this is going to work out by looking at the problem P and checking to see, is there at least one x, not the optimal x, but just any x, that satisfies all of these inequalities strictly. Okay, so I have, I can think about these constraints here as defining for me in X some region that the decision has to live in. Think of it as some convex blob. Okay, and this blob has to have at least one point in the inside of its boundaries. Okay, and if this is true, so if there's at least one X that satisfies the equality constraints, and satisfies all of the inequalities simultaneously with a strict negative value, then P star equals D star. Okay, this is the condition that's most commonly used. And then, okay, actually, we can even make a stronger condition which says that if some of the fi's are linear, then we don't have to worry about those. We only have to worry about the nonlinear ones. And so what that means is that strong duality always holds for LPs because it doesn't have any nonlinear functions. And this is true provided that at least one of the primal or dual is feasible. So an LP is really nice. If you solve the primal and dual and you get a finite value for either one of them, then you're going to get a finite value for both of them, and they're going to agree. Okay? And so this condition, this is called the Slater condition. This is what's more generally called a constraint qualification. It's a condition telling me something geometrical about the collection of constraints in my problem. And if I satisfy this condition, then I know that strong duality will hold. And if I don't satisfy this condition, then there's a big long list of other more complicated constraint qualification conditions that I could check. Okay, but at least for the purposes of this course, this Slater condition is good enough. Okay, so I'll show you now a case where the Slater condition does not hold. I'm trying to convince you that it's, well, how shall I say? I'm going to try to convince you that it's not very interesting when this happens. Okay? So suppose that I have a function, suppose I have a function of two variables. Okay, so I have some two-variable problem. And then I have a constraint that says that x has to live inside this circle, and x has to live inside this circle. Okay, so I have one constraint that says x has to live inside the green circle, and another one that says x has to live inside the blue circle. And so the feasible region would be all of the points inside here intersected with all of the points inside there. And then I should ask, is there any point that's simultaneously not touching the boundary of both of these sets at the same time? Okay, and the answer is no. Actually, there's only one feasible point, and it's the point where my two circles just touch each other. Okay, there's only one feasible point, and it happens not to satisfy a strict feasibility condition on both sets at the same time. If I take this point here, that one does set, it's strictly inside the green ball, but it's not inside the blue ball at all. So it doesn't count as a strictly feasible point. And no point set counts as a strictly feasible point because every point that's feasible is touching the boundary of one of the two sets. So if I were to define now an objective function that I wanted to minimize over this intersection, then in that odd case, the Slater condition will not hold. Normally what happens is I have something instead that looks like this. I have some constraint, some inequality constraint, and some other inequality constraint, and like that. This is similar to a figure that was in the earlier part of the notes. And then so each one of these curves is defined by a function. I have a bunch of inequalities. And the feasible region is everything that's on the correct side of each one of these curves. And then I just want to know, is there a point in the middle? Any point at all? If the answer is yes, then you have strong duality. Okay, and usually this is the case. Okay, so that's what strong duality is. Now I'll try to show you an interpretation of this, and then we'll stop for a few minutes. So suppose that I have a problem with just one inequality constraint. Okay, and I write down all of the locations. I want to write down this set G, which is the set of all u's and t's, where t is the value of the objective function, and u is the value of the constraint function, because I only have one constraint. And I collect up all the points in some two-dimensional figure that I can generate in this way by plugging in all of the x's that I'm allowed to plug in. Okay? So my problem would be to minimize, since I'm trying to minimize f, now what I would think about is trying to minimize t. Okay? But I have to pick a point that I can get to from x, because I have to pick some t that's equal to some f of x, and I can only pick one where the u is negative, because I want f1 to be negative. Okay, so in this kind of weirdly transformed space, the feasible region is exactly this region right here. These are all the points that I can get to by plugging in some argument x, and which give me the u part as being negative. Okay? And now on this figure, I want to solve the primal problem. Okay, so the primal problem says minimize, the original primal problem says minimize f0, which I now take to be minimize t. And it says keep u negative, because I want f1 to be negative. So I say that u and t have to both be inside. They have to both be simultaneously generated by some x, and the u part has to be negative. So that says I have to pick a point on the leftmost part of this blob. Okay, and then I want to pick the point. I want to pick a point where the t part is as far down as possible. So I can imagine taking a horizontal line. Okay, I have a horizontal line extending from over there right up until the vertical axis. And then I just push down this horizontal line until it's just about to fall off the bottom of the figure. Okay, so I have to have the left part of the horizontal line touching this, this blue guy. And I push it down until it's just about to fall off. And wherever that intersects with the vertical axis, that's p star. Okay, that's the primal value. Okay, so now I can say, what about the dual function? Can I think about the dual function in these terms as well? So now the dual function says, take some value lambda, okay, and think about a line that has slope minus lambda. Okay, so here's some minus lambda. Okay, and now, sorry, I should have started up. So I take some minus lambda, like, oops. I take some line up here with slope minus lambda. Okay, and I want it to touch at least one place this blue blob. I want it to intersect with the blue blob in some place. And then I take as the value, g lambda, the minimum crossing with this vertical line. So if I have, if I take a value of lambda which has a very steep slope, okay, I start it off up here, and I push it down, down, down until it's just about to fall off the edge of this graph. Okay, and at that point, I look down through here, and I look at this point, oops. I look at this point right there, and that's g lambda. So I pick a slope, I make a minus lambda sloping line, I push it down until it's about to fall off the figure, and I look at where it crosses. Okay, and so in this case, it crosses right here. And I do that for every lambda. So I take every possible slope. Here's a different one. Okay, I push it down. I get amongst all of those sloping lines a collection of different crossings. And then I maximize the crossing. So what I'm doing is I'm trying to find a plane that's just touching the bottom of this figure and whose intersection with the vertical line is as high as possible. Okay, and you can see, now the point of the figure is that if everything in the function is convex, then the shape G will be a convex set. Okay, so this problem, as I've drawn it, is not a convex problem because it's got this funny dent in it. Okay, and the dent is what allows me to have a gap between P star and D star. If I had drawn the figure with a nice convex shape and I'd gone through the same exercise, then it would not be possible to have D star and P star as different points, okay, provided that the Slater condition holds, okay? And the Slater condition in this figure just says that there's at least one point in this blob that's to the left of the vertical line. There's at least one strictly feasible point, okay? You can try, it's, okay, maybe you want to give it a try. Try to draw a figure which has a convex blob and which does not have a strictly feasible point, and for which P star and D star don't agree. Okay, you can do this. It's not that easy, but you can do it. But the point is that if any part of your feasible G's, if any part of this blob extends just to the left of the line and is convex, then these two numbers are going to agree. And so this is why you get, at least in some kind of graphical form, this is why you get strong duality. Because this shape is a nice shape, and then these 2 points will agree. Okay, so now we'll stop for maybe 10 minutes till, I don't know, 12 past, and then we'll finish. Hi.
Sorry, I have a quick question here. Why exactly is the slope minus lambda? Because we have the G is T plus.
Okay, so what we did with the last slide was we're just talking about what strong duality is, and I said that a convex problem is always, or almost always, a problem that shows strong duality, except in this funny case where you don't have any strictly feasible points. And so what I want to do now is I want to show you some conditions that you can check to see if you have a primal optimal or a dual optimal point. Okay, and these will be the basis of most of the algorithms that you see for solving convex problems. Okay, so let's suppose that I have a problem, some convex problem, and suppose that strong duality holds. So I took my problem, okay, and it's an LP, or I checked that there's a strictly feasible point, and so I know that therefore there must be some primal point, some primal variable x and some dual variable lambda star nu star, such that the two values agree with one another. And so if the two values agree with one another, that means the value of the dual function, which is the thing that I'm maximizing in the dual, has to be equal to the value of the primal function. That's the thing I'm minimizing in the primal. Okay, and now I want to know what conclusion can be drawn about the fact that these two numbers coincide. Okay, so first of all, I take d star is equal to p star. I write p star on the left. That's the value of the primal function, the primal objective function. And I write the dual objective function here, g lambda star nu star. And this is equal to the min over x for that lambda star and nu star of all x's. Okay, because this is the definition of the dual function. Okay, and so if this number is the min over x of all of these functions, then it must be less than or equal to the value of that function when I plug in the specific value x star. Okay, this is what weak duality tells me. It tells me that this, for a particular choice of lambda and nu, which happen to be the optimal ones, they provide a lower bound on this function. Okay, for a particular choice of x. Okay, but I also have strong duality, so I know that this thing has to be equal to that thing. Okay, so now I can just plug in. I know that the primal value, which is p star, or the value of f0 at the optimizer x star, that's equal to the dual function, which must therefore be equal to this thing. Okay, and I make 2 points. One is that this function and that one are the same. Okay, and if I pick x star, that is, if I pick the optimizer for the primal problem, that optimizer has to satisfy the equality constraints. So all the h's have to be 0. Okay, so this term is 0. And I also know that it has to satisfy all of the inequality constraints. So I know that all of these f's have to be non-positive. They all have to be less than or equal to 0. And all of these lambdas have to be greater than or equal to 0. Okay, but still, this number and that number have to be the same. And so therefore, even though some of these entries might be non-zero, the sum of all of these products has to be 0. Okay, and what that means is that if I find in this summation a point where the f is strictly satisfied by the primal solution, so I get fi less than 0, then the multiplier that goes with it has to be 0. And likewise, if I find that the multiplier is positive, then the constraint that goes with it has to be tight. Okay, so either the lambda 0 for each I, or the function is 0 for each I. Okay, I can have both, but I've always got to have at least one. And so this is called complementarity. So if I think of lambda as being a vector, and all of the f's as being a vector, these two vectors have to be orthogonal to each other. Okay, or you have to have element-wise products that are all 0. Okay, so we call this complementary slackness. So this is a feature of any pair of solutions x and lambda nu that give me a primal dual optimal pair. Okay, so if I solve the primal and I solve the dual and I look at my solutions, then every time I get a 0 multiplier, the constraint has to be strictly satisfied. Every time I get an inequality constraint that's tight, the corresponding multiplier is only then allowed to be positive. Okay? So now we can write down a bunch of conditions that tell us when we have an optimal solution. So first of all, if I have a primal optimal solution, that point has to satisfy the constraints in the primal problem. Okay, so I give you some x star, I say this is an optimal solution to the primal, therefore it satisfies the equalities and the inequalities. Okay, so this is called primal feasibility. And then I also have, if I claim to you that I have a solution to the dual problem, then that solution also has to be feasible. And so in that case, it just means that the inequality multipliers have to be non-negative. Okay, and then based on the argument on the previous slide, I have what's called complementary slackness, which means that the lambda, this should be lambda star. The lambda stars and the FIs can't both be non-zero at the same time. The elements cannot both be non-zero at the same time. And then I have one final condition, which is called stationarity, which says that if I take my optimal x and my optimal lambda and my optimal nu, and I plug it into the Lagrangian function, okay, and I differentiate it, then I should find that I have a stationary point of this function. Okay, so the gradient of the Lagrangian, where I differentiate with respect to x, has to be 0. And these four conditions, the primal, the dual feasibility, the complementarity, and the stationarity, if I can give you some point x lambda nu that satisfies all of these conditions, then it's a pretty good bet that I'll have an optimal solution for a convex problem. But it says here, for any problem with 0 duality gap, it should say that on here, if you have any 0 duality gap problem, a necessary condition for optimality is that all four of these things happen at the same time. So if I give you a problem, I say, here's a problem with no duality gap, please solve it. You don't minimize or maximize anything. You just look for a point that satisfies all of these four conditions at the same time. And if you do find such a point, then you at least have some hope. Okay, it's not guaranteed, but you have some hope that it's optimal because these are necessary conditions. They're not sufficient conditions. So there may be, for a non-convex problem, other points that satisfy these conditions, which are not optimal points. And this would happen, for example, if you have a problem with a local optimizer. Okay, so a local optimizer might satisfy these conditions. Okay, but if we have okay, so first of all, let's think now, what does this thing here mean? Okay. So let's think about a problem where I don't have any h's. Okay, I just have the inequalities f, and I have some objective function f0. Okay, so in that case, suppose I have three functions, three inequalities. They define these three blue curves. Okay, and my feasible set is everything on the interior of these curves. So everything in this region here. That's my feasible set. And then if I rewrite this stationarity condition, if I just rearrange the terms a little bit, I would find, again, if I have only inequality constraints, that the negative gradient of the objective function has to be equal to some weighted combination of the gradients of the constraints. Okay, so this is the direction pointing downhill. And these delta fi's, these are the directions pointing out, okay, from each one of the functions. from each one of the constraints. And so what that says is that an optimal point, and by the way, the lambdas are positive. Okay? So now if I look at the gradient of my function at any point, let's take this point right here, I find that the gradient is the function, or minus the gradient, is the function that's pointing downhill. And then I look at the gradient of the two constraints. So one is pointing this way, one is pointing that way. And I'm allowed to take any positive combination of those gradients. Okay? And what I'm trying to do is I'm trying to get some positive combination of those gradients to add up to the direction that faces downhill. Okay, so I look over here. What this tells me then is I'm trying to find a conic combination of these two vectors. So I have a bunch of vectors pointing outward from my constraints. Okay, I think about all the vectors that I can get that are inside the conic hull of these directions, and I get this gray region right here. And I want to check, does the gradient of my objective function live inside? Okay, at this point, the answer is no. So this point cannot be an optimal point. At this point, the answer is yes. And so it can be an optimal point because the gradient is sticking out this way, and it's some positive linear combination of the two gradients of the two objective functions. Okay, now you might ask, why is it that I'm not allowed to include delta F3 as part of this exercise up here? Okay, and the answer is that this constraint, the third constraint, is inactive at this point. Okay, and because of my complementarity condition, since F3 will be strictly negative at that point, the multiplier that goes with it, lambda 3, has to be 0. And so therefore, I'm not allowed to use it when I check to see if this gradient is inside the cone. Okay, so this stationary condition basically just says something like the gradient of the function is pointing outside of my constraints. That's all it says. Okay, if it were pointing inside, then I would have some hope of improving. Or in this case, it's not inside the constraint, so I can sort of slide along this blue line and get somewhere a little bit better. Okay, so this is a slightly cartoonish geometrical interpretation of KKT conditions. Okay, so now for a convex problem, these are really nice. Okay, so for a convex problem, if I suppose that I have strong duality, then if I can find any combination of primal and dual variables that satisfy these conditions, then P star is equal to T star. Okay? And so I know this because the primal value is equal to F0, and I know that's equal to the Lagrangian because of the complementary slackness condition. And the dual is equal to the dual objective function, which is also equal to the Lagrangian because it's a convex problem and I have the stationarity condition. Okay, so therefore this guy is equal to L evaluated at that point, and D star is equal to L evaluated at that point. Okay, and if I have the Slater condition, okay, then I know basically all the planets are going to align and everything's going to work out great. And if I solve the KKT conditions, then X star is optimal if and only if I can find some lambda and nu star that satisfy the KKT conditions. So what this says, or what this amounts to, is if I go back to these KKT conditions here, if I give you a convex problem, I tell you the Slater condition holds or some other constraint qualification holds, then all you have to do, a necessary and sufficient condition, is to solve these equalities and inequalities. And if you've solved them, then you have the right answer. Okay, that's the thing that you should take from these three slides. If you don't have a convex problem or if you don't have some constraint qualification, then you have to think a little harder. But most of the time with a convex problem, you do have some constraint qualification, and all you have to worry about is solving all of these conditions. And that's it. And most of the optimization methods that we have for solving convex problems come down to, instead of minimizing something, just trying to satisfy these KKT conditions. Okay, so now what I'll show you is just an example of writing down the KKT conditions, and we'll see what they look like. So suppose I go back to my quadratic program, and I take, again, Q being, okay, this time positive semi-definite. I could take it positive definite if I want. So I minimize this objective function subject to this equality constraint and this inequality constraint. And now what I want to do is I want to write down all the KKT conditions for this problem. Okay? Here's my Lagrangian. It's the objective function from the original problem plus some weighted combination of the equality constraints with the weights of the equality multipliers, and then minus lambda times x. And the reason why it's minus is because I always want all of the constraints to face, or sorry, all of the inequalities to face to the left. So I should write it like that. Okay? So I have here minus lambda transpose times x. This is my Lagrangian. And now my my four conditions are that I have to have primal feasibility. So the constraints in the primal problem P have to be satisfied. I have to have dual feasibility. So the lambdas have to be greater than 0. And then I have to have complementarity. So complementarity said something like Fi x lambda I is equal to 0. But in this case, the functions Fi x, they're just the individual components of x. Those are the things I'm constraining. So, or sorry, minus that actually. But the products have to be 0, and so I get this complementarity condition. Okay, and then the last piece that I need is to just differentiate this function with respect to x and set its gradient to 0. So I get this guy here. Okay, and the last condition at the bottom, which says, now note that the x is non-negative and the lambda is non-negative, and that means that the element-wise products have to, well, actually what I want is that the element-wise products have to be 0, okay? But because the vectors are actually all non-negative anyway, I can actually say in this case that x is orthogonal to lambda. Or if I take the inner product of x with lambda, I should get 0. But it's only because none of the terms are ever negative anyway. So I don't have to worry about terms canceling out. Okay? So I would write these last few conditions here. Sometimes you see it written in this funny kind of composite form, which is actually 3 separate conditions. It's x bigger than 0. It's x perpendicular to lambda, or the element-wise products are 0, and also lambda bigger than 0. Okay? Now, so the claim is, if I can summarize the KKT condition claim, the claim is that if I want to solve this minimization problem, okay, which is an optimization problem, instead all I should do, okay, instead's a bit strong, it's not that easy, okay, but what I should do as an alternative is I should try to solve this system of equations and inequalities, okay? And this would be really easy were it not for these two guys right here. Okay, if I didn't have the two inequality conditions, I would just have a big linear system to solve, and I would solve it and I would have the right answer. Sadly, I don't have that. I have these inequalities. So I have here a big region which I can think of as a plane that's defined by this one, I'm sorry, just those two. Oh, no, sorry, I misspoke. This is the really nasty one right here. Okay, so I have a big region which is defined by a plane. Those are the first two conditions. And then I say that I'm only allowed to take positive elements of some of the components making up the function defining that plane. But then I say some of the vectors have to be perpendicular to one another. And, okay, this is really not that nice. I mean, having a constraint that says the two things are orthogonal to one another is not in any way smooth or convex or anything like that. But the point is that there's nothing to minimize here. It's just a system of equations and inequalities that I have to satisfy. So when you come to the optimization part of the course, what you'll see is that the optimization techniques that we use usually come down to just forgetting about this one and solving this one instead. Okay, and in particular, if any of you've seen interior point optimization, which is what you'll talk about in a few days. An interior point solver is just a solver for constructing a solution to this set of equations. Okay. Right, so now, okay, I'm going to skip this bit. So there's 2 slides here which show something about, well, okay, I'll do it. So you have, I will do it. You have a problem. So I said sometimes it makes sense to keep things in the domain of the function, and sometimes it makes sense to keep them as explicit constraints. And so I just want to show you that it really doesn't make any difference which way around you do it. Okay? So I'll show you by constructing the dual of this problem in 2 different ways. And this is more of an exercise so that you just see a few more times how one goes about constructing a dual function. So first of all, I'll take it. So what I want to do is I want to minimize a linear function subject to this equality condition, and x lives in a box. Okay, that's my problem. So I write down the dual function, and first I write it with 2 different explicit inequalities. So x less than 1, and then minus x less than 1. I form my Lagrangian. For each side of this inequality, I require a different multiplier. So I have the left-hand side inequality multiplier and the right-hand side inequality multiplier. And I call it x under bar and x over bar. Okay, so I minimize all of this over x, which means that I should collect up all the terms with x in them. It will be some linear function, and I'll find it's actually this thing times x. And so therefore I conclude that this collection of terms has to be equal to 0, otherwise the dual will be minus infinity. So my dual function is this guy whenever this is true, and it's minus infinity otherwise. So then I construct my dual problem by taking this constraint, or this definition of the domain of the dual function, and making it explicitly a constraint here. My multipliers have to be non-negative, and I have an objective function to solve. Okay, so I did it quite quickly. You can just, on your own, see if you can reproduce all the steps. It's very mechanical. Okay, so what I did here was I took my box constraint as an explicit constraint, and I ended up with 2 multipliers that go with each side of that constraint. And I end up also with a multiplier for the equality. That's this new guy here. Okay, now instead what I can do is I can say, well, this box constraint I instead take as the domain of my function. Okay, this problem is identical. I've just written it in a different way. But then the process that I go through to construct the dual is a little bit different. So I minimize this function only over the box, subject to living in this plane. And so now my life is a little bit easier, because when I write the dual, all I need to do is the objective function plus the equality constraint, which was ax minus b equal to 0, because I always want a 0 on the right, times the multiplier. But now when I do the minimization, I have, instead of minimizing over all x, I minimize only over the box. So if I want to minimize over this box, I should collect up all the terms here in x again, and I would get a transpose times nu plus c all times x. And I minimize that over a box, which is the same as taking minus the sum of the absolute values of this vector. Okay, so here's my dual function. So now my dual problem is this. It's an unconstrained problem. Minus b transpose times nu minus this 1 norm term. And so something seemingly weird happened. Okay, I had this primal problem, which I claimed was the same as the one on the previous slide. I go back to the previous slide. I ended up with this elaborate-looking dual problem with all these constraints and variables. Okay, but now I take my box constraint, I put it into the domain, and I have now a maximization problem which has no constraints. Okay, so what happened? What happened was that this is not a linear program. So if I want it to be a linear program, I have to add some variables on either side of this term. Or sorry, I have to say that this is equal to the sum of some positive components minus some negative components. I make all of those components non-zero, and then I add up those bounds. So I just have to do some tricky reformulation to make this thing look like a linear program. And now it turns out that this problem, if you look back at the other page, this problem is identical to the one on the previous slide. Okay, so in the end, I always get to the same place, but I guess it's a matter of preference. This I find a little bit easier, but If you're not comfortable having the minimization in there, then you do it the other way. Doesn't matter. Okay, so now we come to the last bit, which is something about sensitivity. So I said to you that if I want to solve my convex problem, what I can do is I can just write down the KKT conditions, and I solve them. I get x star, I get lambda and nu star. And what this means is that I have a solution of the primal problem, and then the lambda and nu star at the same time give me a solution to the dual problem. And okay, this is nice, I suppose. You have a solution to two problems, but it's not really clear yet how the two solutions relate to one another. Or specifically, what does the solution to the dual problem tell me about the primal problem, if anything? Okay, so we can make some statement about that. So we can say, first of all, let's write down the primal problem. Here it is. I have assume that it's convex, and assume even that it has strong duality. Okay, so it has some objective function. It has some inequalities and some equality constraints. And then I apply all my machinery, and I end up with the dual problem. So G is min over x of the Lagrangian of this problem, whatever that happens to be. So for the moment, it doesn't really matter. So the point is I have the dual function, and I want to maximize it subject to lambda being bigger than 0. And suppose that I could solve these two problems, and suppose that their values agree. Okay, so now let's take this problem on the left, and let's ask what happens if I just tweak the right-hand side a little bit. Okay, so I either make this inequality a little bit tighter by making the right-hand side a little bit negative instead of 0, or I make it a little bit looser by putting on the right-hand side a positive number. Or what happens if instead of having hx equal to 0, I make it equal to epsilon, or actually v, as I've written it here. Okay, so then what I can do is I can say, well, suppose that I just move the right-hand side about, and I move the right-hand side of the equality about, and then I can ask, what's the dual function? Well, I should rewrite this problem such that everything ends up on the left. Okay, so I should rewrite it as fi minus u less than 0 to get it into my standard form. And then when I take the dual, I would find that the multiplier that previously multiplied f by itself now multiplies f minus u. And so in the dual problem, I just get the same problem as before, but I have u times lambda appearing as an extra term in the objective. And I get v times nu appearing as an extra term from the equality for the same reason. Okay, and so I said that my primal optimal solution, this guy has value p star. Okay? I'm going to take the value of the perturbed problem to be p star, but now it's in a sense parametric. It's p star of u and v. Okay, so it's the value of the primal problem that I get when I adjust the right-hand sides by the amount u and v. And so what that means is that the value of the original problem is p star 0, 0. Okay, and so now what I want to know is how does p star change as I manipulate u and v? And the dual optimal solution will tell me at least partly the answer to this question. Okay, so assume that I have strong duality. And so I have p star, oops, yikes, what did I just do? I have p star equal to d star, strong duality. Okay, p star being the unperturbed optimal. Okay, then if I have strong duality in the problem that I start with, if I perturb it a little bit, there's no guarantee that I will maintain strong duality. Okay, there's no reason why I should believe that this should happen. It seems kind of plausible, but I can't guarantee that it's going to happen. So for the perturbed problem, the only thing that I can guarantee is that the primal optimal solution or value for the perturbed one will be bigger than the optimal value in the dual. So p star when I inject a perturbation u and v should be bigger than the dual optimal value for the perturbed problem. Okay? But what I have here, g star of nu star and lambda star, this is just the unperturbed primal optimal value. And then I have these extra two terms on the right. Okay? And you can see that they're the perturbation times the multiplier. Okay? And so now I can ask, what happens if I change the right-hand side? So I might say I have a problem. It has these constraints, and I solve it. Oh, the optimal value is not so good. Maybe I'm willing to loosen up a little bit the inequality constraints, say. Okay, so then I can conclude from the argument here that if the multiplier that goes with my constraint is large, so first of all, I should only worry about loosening the constraints which are actually active at the optimal solution. Okay, and I know that they're active because they will have non-zero multipliers. Okay, so I find all the constraints which are actually satisfied with equality, the inequality constraints which achieve equality, and those are the only ones that can have non-zero multipliers. Okay, and I look at all the ones that have multipliers that are large, and I say, well, if I make the constraint even tighter, then I know for sure that P star is going to go up a lot. Okay, it's going to go up a lot because of this term right here. Okay, now this is not to say that if I loosen the constraint, it's not to say that the cost will go down a lot. Okay, and the reason is because I don't have equality here, I have an inequality, okay? Because I can only guarantee weak duality in the perturbed problem. So if I loosen things up a little bit, it may be the case that I just end up introducing a duality gap, okay? But if we assume that that doesn't happen, then we could make a sort of, we would have a kind of symmetrical hope anyway, that if I loosen up the constraints for the constraints that have big multipliers, I hope that the situation will improve. But definitely if I tighten the constraints, the situation will get worse, okay? And if I can also say that if the multiplier is very small, if I loosen up those constraints, then it's not going to do very much to the value. This is all I can say. This is all I can guarantee anyway. Okay, and I can make a similar argument about the inequality multipliers and the equality multipliers and the equality constraints. Okay, so if I have a very large positive multiplier and I shift everything sort of to the left by adding a negative term onto the right-hand side of the equality, then the cost is going to go way up. If I take exactly the opposite situation, so I have a very small one, and I loosen it to the right, then the cost isn't going to go down very much. So this is, in a sense, not that great because it's only telling me how to make things worse. It's not really telling me how to make things better, but it's at least giving me a hint about how to make things better. Okay? And the only reason why it's not telling me explicitly how to make things better is because I have this inequality here, this switching from strong to weak duality. Okay, and so that's what this means then here. It's not symmetrical because we only have a lower bound, because we only have weak duality. Okay, but this is kind of pessimistic, so the last thing I'll show you, this is the last one, is that most of the time, the situation is a bit happier, okay? So most of the time, so assume that strong duality, so I have here the same thing as before. But now suppose that this function P star of u and v is actually a differentiable function. Okay, so the value of my optimal solution in the primal is a differentiable function of the amount by which I manipulate the right-hand sides. Okay, just suppose that that's a differentiable function. Then what I would find is that if I do actually differentiate that function at the point 0, or if I sort of linearize, if you like, about the nominal problem, then the inequality multiplier tells me exactly the amount or the rate at which the cost will change. Okay, so I have to assume that it's differentiable for this to be true, though. Okay, so if I have a really big positive multiplier and I manipulate the right-hand side of the inequalities for a differentiable function P star, then the cost is going to go way down. And if I make it tighter, the cost is going to go way up, at least locally, okay, for small changes in U. And likewise for the equality multipliers. Okay, so now if I draw for you a little figure, I have here U going in this direction. I have the optimal value going in that direction. And there's some kind of curve of optimal value as a function of the changes or the relaxation or the tightening of the right-hand side. And if this happens to be a nice curve, then I differentiate it, and I get locally P star 0 minus the multiplier, which is the slope of the line, times the amount by which I moved it. And so I can think of the lambdas as the sensitivity of the cost relative to changes or tightening of the inequalities. And if I find that the lambda is 0, that means I basically don't care if you change the right-hand side of the inequality, and that's because the inequality isn't tight anyway. Okay? But if it is tight, and also the multiplier is non-zero, because it's possible to have an inequality that's actually 0, but the multiplier is 0 anyway, which means that if you move the right-hand side around, you're not going to get any improvement. Okay? But if you have a non-zero multiplier, that means you know the constraint is tight, and if you loosen it or tighten it, you're going to change the cost. So when you solve your problem, what you should do, or when you ask MATLAB to solve your problem, what you should do is you should look at all the multipliers, and if one of them is standing way out, then you know that that constraint is the one that's driving most of the cost. And you should ask, is it possible to loosen this up a little bit in some way? Okay, so I didn't tell you anything about solving the problems. That will all come in a few days. But tomorrow, what you'll do is you'll start to take your optimal control problems and try to write them down as convex problems. So you won't see me for that, so I wish you luck in doing that. And thanks very much.